I2S audio and DMA is a mysterious world. What are these parameters DMAbufcount and DMAbuflen? What are they for, and what values should they be set to? Let's try and answer these two questions. Before we get started, I'd like to thank PCBWay for sponsoring the channel. PCBWay offer PCB production, CNC and 3D printing, PCB assembly, and much more. They are great to deal with and offer excellent quality, service and value for money. Check out the link in the description. Since we're looking at audio, I'm going to focus on streaming sample data to and from the CPU to I2S peripherals, generally microphones and speakers. We'll start off with a definition of what DMA is. DMA stands for Direct Memory Access. DMA allows peripherals to directly access the system memory without involving the CPU. When using DMA, the CPU initiates a transfer between memory and the peripheral. The transfer is all taken care of by the DMA controller, and the CPU is free to go off and do other work. When the DMA transfer is completed, the CPU receives an interrupt and can then process the data that has been received, or it can set up more data to be transmitted. This gives us our first data point on how to choose a size for our DMA buffer. Small DMA buffers mean the CPU has to do more work, as it will be interrupted more often. Large buffers mean the CPU has to do less work, as it will receive fewer interrupts. Taking audio as our example, suppose we are sampling in stereo at 44.1 kHz with 16 bits per sample. This gives a data transfer rate of around 176 kilobytes per second. If we had a DMA buffer size of 8 samples, we'd be interrupting the CPU every 181 microseconds. If we had a buffer size of 1024 samples, we'd be interrupting the CPU every 23 milliseconds. You can see this is quite a large difference. So the naive conclusion from this is that we should make our DMA buffers as large as possible. But there is a trade-off here, and that's latency. We need to wait for the DMA transfer to complete before we can start reading from the buffer. Generally, with audio, we don't really have hard real-time constraints, but you can easily imagine a scenario where a delay of 23 milliseconds could have a real impact on your application. But what are the actual limits on the values for DMAbuflen? It's easy enough to test, and we get a very helpful error message when we try something very large. We can have at most 1024 and must have more than 8. One interesting thing to note is that this value is in samples, so to calculate the number of bytes that are actually being used, we need to use this formula. The number of bytes per sample, multiplied by the number of channels, the buffer length, and the buffer count. So in a concrete example with 16 bits per sample, stereo left and right channels, buflen set to 1024, and buff count set to 2, we have a total of 8K allocated. There's another good trade-off to talk about here. DMA buffers are allocated from memory, so any space we use for DMA buffers is taken away from space that can be used by the rest of your code. There is also a limitation that DMA buffers cannot be allocated in PSRAM, so we are limited to the internal SRAM of the chips. This limits us to a maximum of 328K. In testing with my walkie-talkie application, I managed to allocate a total of around 100K before the application started to run out of memory and crash. This leads us nicely onto a discussion of what to set DMAbufcount to. Let's break this question into two parts. The first part is, why do I need more than one DMA buffer? The second part is, how much total space do I need to allocate to DMA buffers? Remember that we are limited to a maximum of 1024 samples per buffer, so to have more space, we need to have multiple DMA buffers. Let's answer the first question. Why do I need more than one DMA buffer? The problem with having only one buffer is that it does not give us any time to process the data. Without some serious hacking around, the DMA buffer can only be used by either the CPU or the DMA controller. They cannot access the buffer at the same time. This means that we can only start processing the buffer once the DMA controller has finished transferring data to it. If we only have one buffer, we need to complete our processing and give the buffer back to the DMA controller before any new data needs to be transferred. With a sample rate of 44.1 kHz, we only have 22 microseconds before the next sample comes from the device. This is not very long. It's unlikely we could do anything meaningful in this time. Our processing task may not even be scheduled quickly enough to even catch the data. The result of this means that you typically want to set the DMA buff count to at least 2. With 2 buffers, you could be processing one buffer with the CPU, while the other buffer is being filled by the DMA controller. So we definitely need more than one buffer. Let's move on to the second question. How much total space do I need to allocate to my DMA buffers? To understand this, we need to think about the components of our system. We have the I2S peripheral that is generating samples from our audio source. This will be generating data at a fixed rate that is set by the sample rate. We then have something that is consuming and processing this data. To understand what we need to set the total buffer size to, we need to understand how much time this processing will take. Suppose, for example, we are sending data to a server somewhere, and the server takes on average 100 milliseconds to process a request. Sometimes it's faster, sometimes it's slower. 100 milliseconds of audio at 44.1 kHz sampling rate works out at 4,410 samples, or around 17 kilobytes of data for stereo 16-bit samples. This sets a lower limit on our DMA buffer size. We need space to store 4,410 samples while we're busy sending the data to our server. We also need to allow for the fact that sometimes our server takes longer to respond. What if it sometimes takes 150 milliseconds to respond? We need to allow a large enough buffer size to take this into account. 150 milliseconds is 6,615 samples. For a safety margin, we might just bump this up to 10,000 samples. So we might set our DMA buff length to 1000 and our DMA buff count to 10. I've made a small visualization of this. We have a constant stream of data being generated, which is going into a buffer, and we have a process that takes chunks of data from the buffer at semi-random intervals. We need to make sure our buffer is large enough that the probability of it overflowing is low enough for our use case. So this covers the case of processing audio data coming into the system. What about pushing samples out? How should we think about this? We now have something that wants to be fed samples at a constant rate, and we have a source of samples that may not be able to consistently push samples into the buffer. To think about this, we need to consider how quickly on average we need to generate samples, and we need to think about what the worst case delay there could be in generating those samples. How quickly we need to generate samples is set by our sampling rate. If we cannot generate samples fast enough to meet our sample rate, our system is not going to work. No amount of buffering will help us. Unless, of course, we can generate all the audio data up front in one very big buffer. An example of this as a solution would be to load an entire audio file into memory from slow storage and play it directly from RAM. Assuming we can generate data fast enough for our sample rate, we need to think about the length of random delays that may mean we can't deliver some samples exactly when the output requires them. A good example of this is from our walkie-talkie project. We are playing samples from a stream of UDP packets. Depending on network conditions, our packets will be delayed by some variable time. We need to have sufficient headroom in our buffer that our sample sync does not run out of data when there are delays in delivery. Taking our UDP example of 1436 bytes once the header has been removed, which is 718 samples, we would need to queue up at least this many samples into the output buffer. To allow for packet delays, we might want to have a buffer of twice this size so we can queue up 2 packets before playing. Once again, some safe values for this might be 2 to 3 DMA buffers of 1024 bytes each. One last point to think about is that we can also have buffers in our application code. We don't need to rely solely on DMA buffers to solve our problems. You may choose to have relatively small DMA buffers and use your own buffers to handle things. There may be some good reasons for taking this path. You may have multiple different processing steps, some that require very low latency and some that have quite variable time delays. The low latency requirement forces you to use quite small DMA buffers, and then have your own quite large memory buffers to handle the variable time delays. So hopefully this has given you some insight into how to choose values for these 2 parameters. As always with these things, the real answer is, it depends. But there is some guidance. Use DMAbuflen to trade off between latency and CPU load. A small value improves latency, but comes at the cost of more CPU load. Use DMAbufcount to trade off between memory usage and the total amount of buffer space allocated. More buffer space gives you more time to process the data, but comes at the cost of using extra memory. Now I need to go back to my code and check all the values are correct. Thanks for watching. I hope this video was useful and interesting. I'm sure it will spark some lively debate. I'll see you in the next video.